Alright, welcome back. And I am sitting in front of a mirror because I need a power outlet, because a lot of my problems I had were due to the lack of a scope, which I resolved, and also due to power supply problems. I now have an external power supply, so I hope I get enough power for what I want to show, which was writing the EEPROM, correctly forming the pulse, and I have my Arduino here, which is no longer providing the power. So I have only the ground connected, so they have the same reference ground, but the Arduino runs on its own power and is not running on the CPU power, and the CPU runs on its own power. Right now, I did a little test before, but now the Z80 monitor has started up. Right, there we go. And I'm going to fire up the CPU, and we can see that we're now in this weird state, pre-reset. Okay, very slow clock. I've also improved this clock here. Very slow clock, and we're running in requiring a reset in order to start. I'm going to reset, and you see the start sequence just like we had it. If the stupid thing can stay focused. Yep, it cannot stay focused. I don't know why. But you can see, if I can stay focused, you can see how we are waiting for input. And what I want to show you is how I write to ROM. And I'm going to cut to the chase here, not to do all sorts of tests before. What I wanted to do first is I'm copying my my service routine, which is in position 0100, right? And it's a very short thing. And I want to copy this to 8000. That's where I want to run it from. Okay, so now this is starting to do its job. It looks good. I think we can turn off monitoring and crank up the speed, or rather we crank up the speed and then we turn off monitoring. All right, so I crank up the speed, Now it does its thing, and actually it already is done, right? So this was fast. But now I'm going to turn off the monitoring, because now I will just prove to myself, read from 8000, that's RAM. Read from that, I see what looks like my service routine with this 3E3E. I can now jump to that position, and now I'm outside of the ROM. Okay, I've displayed all the other ROM modes before. I just haven't displayed the write mode. So let's just take an area of the ROM, which hopefully is not going to, which is not a problem for us to write to. So let's read from position 1000, just in the middle of the ROM, and let's read this. And what we see is an empty space. Empty, right? It's been wiped. That is good. I don't want to do too many other things. All I want to do now is write in here my service routine. Okay, that's all I want to do. And the way I do this, cutting right to the chase, okay, is that first of all I need to focus. Is that I take this. This line was the negative. The inverted. It was the inverted right enable line, right? This right enable line is always like, I don't know if it has a good contact. I hope it does. Maybe I show it on the scope, but right now I want to show the practice. Then I can maybe just leave a short video that just shows that it works now and be done with it, because I'm having lots of power problems, including the power in this hotel going out all the time, and I don't want that to happen now. So what I'm going to do now is I take this and I say, hey, ROM always on. Do not turn off the ROM just because we're trying to write, okay? The next thing I'll do is I will hook up the right enable line of the ROM, which is very securely in here. Sorry for that. I'm hooking that up. It's weird. It's weird. I'm going to use my hands now. I'm going to hook this up to the output of the low going right pulse. Oh my gosh, come on. Okay, hooking this up to the output of my low going right pulse, which is right here. This is the output. I'll explain the circuit in just a moment. All I want to do now is, okay, I think I have it connected correctly now. I want to just read again. Read from 100080. And you see, it's still that. And now I want to write my service routine, which I already copied out into 8000, right? That's what I'm running from. Okay, and I want to write this into the ROM. And crossing the fingers, not crossing the fingers, actually just face palming me, because I used W, and that's the writing. And I can't, this is so dumb. Okay, I'm going to just not fiddle anything. I'm just doing something else. I'm just writing zeros, okay? So I put my hand on the 0, and I hope that the repeat, oh no, oh no, oh no, I need to actually, I need to emergency basis go back, not writing to the ROM. Sorry, not write to the ROM. Do not write to the ROM. Okay, and now I think I can just reboot everything. Okay, I'm gonna reboot everything, meaning I will go back to the monitor. Okay, I will go off the reset button, and fortunately I'm back. I didn't destroy anything, and just going to 8000 now. That's still all in memory, nothing was wiped out. Go. Putting this now back, I want to show the writing. Oh my god. And this, I have to use the C command, C for copy. Don't forget this. Don't say W because I save writing, but really I want to copy. This write function doesn't even work correctly in the Arduino code, but I don't care about software. Okay, I got it connected correctly here. And now I go straight to copy. And I typed something wrong again, which probably won't work. So let's just copy something else. Copy from whatever. 0000 01 bytes to 9000. Okay, I think this is good. Nothing bad happened. So now please, without typo, I want to copy from 8000. I want to copy 128 bytes to position 1000, which is the ROM. Okay, go. And it's done, okay? That's the ROM. Now I can read from ROM. Read 1. This is the moment of truth. And you see, I wrote to ROM. I wrote to ROM, and I will show you this, because now I'm going to turn off the write line because I don't want to destroy the ROM because of some stupid typo that I make. So I'm going to just turn off the write. I put it to mandatory. This is the write lock, if you will, okay? So now nothing can write to the ROM anymore. I'm going to go back because I'm going to restart from scratch, power off, okay? Going to back into the normal mode where read from ROM, write to RAM, and I will turn off everything, okay? So now you see all the lights are off, so we're now without power. I can show you that the memory, the RAM is on the position 8000, right? It's going to be garbage when I turn it back on, but what I wrote into 1000 is going to be there. Turn on. Gotta restart this somehow. You see I'm at halt, that's good. So I can hit this, reset. I'm going to turn off the monitoring and read from position 8000 80 to demonstrate to you that the RAM was not deleted. And I read from 1000 and the ROM also is not deleted. But why is the RAM not deleted in all the world? I'm going to disconnect again. I'm going to disconnect this power as well. I'm going to disconnect this power because it might be that just because of a minor capacitor that was still full of power, the RAM now might have preserved its state. I mean, it's such an unusual situation, but let's do it again. So I can connect, my monitor will come back, CPU still off, power being connected. We're now in this weird state where we are reading a bunch of bytes that have nothing to do, and M1 doesn't come on. I'm going to turn this off right away, and I'm going to hit the reset button, and we immediately started correctly. Now I'm reading again from 8080 bytes, and now you see how it's all garbage, right? It doesn't look like RAM garbage because it's FF. Normally RAM garbage I know is 00, but clearly this is garbage, okay? And now I'm reading from ROM, and you can see my service routine is right in here, and I can jump to the service routine and it will work, okay? It worked. And I can copy my service routine, which is now at a different place. I can copy this to 8000, okay? And I can jump to 8000, okay? And it works. So, thankfully now, I have been able to demonstrate, I have come through with my promise that I will fix this and it will work, and I can now use a few more minutes. Maybe we can make it this shorter video than normal. I can now use a few more minutes to just show how this works, okay? Now, how can I do this? I need to come to a situation where we are writing constantly, okay? And then I will show you on the scope, while I eat my cucumber, I turn on the scope, all right? And with luck, I won't have the same mess that I had before. If I have mess, if it doesn't work, I'm going to give up on the scope and I just show the theory. But I do a lot of theory, and people don't. I wouldn't like to see my own video that only has a theory. So I should be looking at my clock. Okay. But I'm not happy at all what's going on here. This is not good. And I have no idea why. Oh yeah, I do. I actually, it's still good. I have to drive from channel 1. Channel 1 is now showing as negative. Why is this? Actually, I'm going to disconnect. I'm going to disconnect the computer, and it turns out that when I have the computer connected, the scope gets totally confused. It considers if I have this connected and the computer connected, right? This power supply and the computer, then it will not, it will completely, I don't know what it's doing. So I think what this means is I will not be able to actually show the scope picture that shows the, you know, I can see my clock. I will probably just show my clock. The rest will start. See my clock. Okay. It's running in frequency 2 kilohertz now. This is the maximum frequency. Okay. And what I'm going to do is I'm going to show you how I turn the frequency down. I turn it down by screwing here in this knob. You see how I'm making the clock cycle longer and longer, but I don't change the low phase. The low phase stays stable. And I adjusted this to be even more correctly in the range. So that, as you can see, I'm making this more so we can actually measure it. Okay, you can see now it is 131 microseconds. Here, there. Come on, be visible. Be visible. 131 microseconds. Okay, so that is good. And now, the low going pulse. I'm going to explain it because I don't want this video to be too long, and I'm pretty annoyed about the many things that have gone difficult. I don't understand why as soon as I plug in the ground, to have the same ground as the computer, my scope suddenly thinks everything is reversed. Look at that. It's like everything is reversed suddenly. And I don't even know whether this might break something. Here, look at that. As soon as I hold the ground, which is really just, it should just share the same ground, but somehow the scope, perhaps the scope is actually working the opposite way. I don't know. Ground and power is inverted, and I don't understand, and it's driving me nuts. But I'm not going to actually show what's happening here, and I don't need to, because you've seen practically that I was able to write, and that's all I wanted to show to finalize my report. Now I'm going to explain how I do it, okay? And it's kind of important if somebody wants to do something similar. What I showed you last time, in the last part, is not only not working, it is actually capable of destroying the chip. It is not, what I drew is not even actually what I did, so maybe I shouldn't even show. It might be good, because somebody who would have done what I did would not be able to have gotten it to work, nor would it actually destroy the chip. But I'm going to show here on the stack exchange thing where I got into an argument with the moderator. You know, they are sticklers, and then I've been blocked for 3 days, and I might get myself blocked from this site entirely because these people are crazy, these moderators. But anyway, let's show what I did, what Ben Eder did. This is Ben Eder's circuit. This is what he showed us in his EEPROM programmer that went manually. When I built this with that switch button, and I had it on very slow mode, and whenever the right light came on, I actually hit the button. That way I was able to write into this ROM. So Ben Eder's circuit kind of works, but it is dangerous because what it does, I'm trying to keep it focused, because what it does is it will cause not just a low pulse, but on the other side, when you release the button, it causes a high pulse twice twice the VCC, twice the power rail. The power is at 5 volt, and so if you release the button, it goes up to 10 volts. And with that, I have destroyed a Schmidt trigger inverter input. Got hot, and it's all destroyed now. So this is dangerous. This should not be hooked up to the memory. Dangerous. Even with a button, where you just do it a couple of times, you can actually destroy a chip. The reason why we can't quite destroy the EEPROM is, I believe, because they are actually, some of the pins can be driven at 12 volt, and that's the chip select or the output enable. For a complete erase, quick erase, you can actually drive it at 12 volt, and this is probably why the memory did not get destroyed, and why Ben either couldn't destroy his with this circuit that he has, this one. But it's a bad circuit. Don't do that. What is a good circuit? A good circuit is this, the one that I ended up building, and there was a good person. Stack Exchange is full of good people, and the moderators and whatever other sticklers for the rules are just annoying. They're like, I tend to do a lot of work, right? They say on Stack Exchange, oh, you shouldn't just make a quick question, you should actually show your work. So I show my work, and then people go, well, they go all confused, and then they accuse me of, this becomes a chameleon question, and it's all about the same issue. It's just trying different ways of doing it, and validating what people are telling me, and answering questions, and so forth and so forth. But this was the best answer. This is really cool. Why is this good? It is good because I'm already taking my write signal and I'm already inverting it, right? I do that for this for the chip select or cascade, right? So I already have an inverted write signal. So this approach here requires me only one more inverter gate, okay? And it's connecting. He has 220 picofarad, and he uses Schmidt trigger, CMOS HC Schmidt trigger inverter. I tried all the different inverters, Schmidt and non-Schmidt, LS and HC, and I have discovered that it works just fine with LS 04, with a normal inverter, which I prefer because I can then reuse it. It works nicely as a medium speed oscillator. 2 megahertz, 1 megahertz, even 4 megahertz works well, or less with a capacitor. So that's why I like to use the LS 04, not the Schmidt trigger. And while theoretically, when you have something that is slow or weirdly wobbly rising edge, you should be using a Schmidt trigger inverter, a Schmidt trigger input that will then straighten it, right? Because of the hysteresis. So in theory, this should be better, but in practice, LS04 works just fine. I'm using a 470 picofarad, which gives me just about 5, and I use 1 kilo ohm here and 1 kilo ohm here. And with that, I get a 500 nanosecond pulse, which after this inverter goes up, but then the last inverter stage just makes it a low pulse, right? And this is how I wired it up. So here is the right signal from the CPU that gets inverted and then goes into my OR cascade here. And then I also have this 470 picofarad capacitor, which then goes into this file of contacts with 1 kilo ohm to ground and 1 kilo ohm over into the input of the last inverter stage. And then you saw me connect this here. Now it's in write protected mode, and if I connect it to the write mode, I could actually write the EEPROM. So I'm now able to do a firmware upgrade without with enough security that I don't ever again brick my EEPROM, and I don't have to take the EEPROM out anymore to program it. So I'm very happy with this. Yeah, I finished this project here. I don't want to I don't want to waste any more time on this right now. It's come to the desired conclusion. I have a few erratas talking about mistakes, things that I said wrong in my previous couple of videos. But I think most of it is superseded now by what I did now. I guess my biggest blunder was that I said, oh, there are 3 outputs here from this final OR gate, and that has something to do with the writing. It doesn't have anything to do with the writing. This output here is just showing the chip select light, which I use for slow debugging. Okay, yeah, generally power problems, running LEDs directly on the inputs is a problem. Even with the resistors, I mean, these are they drag quite a bit of power. That is its own issue. I had explained how I used the 555 timer and how I used the low pulse I had at 1 millisecond, which is way too long. But this problem is exacerbated if we are running low on power. I think right now in the 3rd take of the video today, I have resolved the power issue by separating the at least separating the positive side, but the scope causes all sorts of weirdnesses if I run the scope from the same computer power as I run this here, while that comes from the I don't know why this is all inverted or whatever. I have no idea. But another thing that I was saying is that and that was kind of wrong. I used a 74HC32 OR gate here, and I used the 74LS inverter, LS04 inverter. When I put it's actually incompatible. You shouldn't use LS and HC. You should use LS and HCT if you want to combine them, which is a mistake I made. I need to buy HCT chips as well. But I went back to use the LS here, the 74LS32. It takes the issue that I had with this was a power issue with this external power supply. That is resolved. Now I could not use the 74HC04 here. Why? Because the NMOS Z80 at this difficult power situation, all running low on power, was not able to actually drive this inverter here, and this was causing all sorts of trouble. So now this is supposed to run with LS, 74LS, and so now I have all LS everywhere, and I just have to depend on this external power in order to run this. I have lots of work to do, and I don't have time for this to continue this for the next few weeks, and I won't. Just need to get this video out in order to just forget about it anymore. I've been able to do what I wanted to do. The next steps would be to actually replace this Arduino here. The Arduino constrains me in frequency. While it's really cool, I was able to monitor exactly what was going on the bus. This is a really good lesson. I learned a lot. It's really cool to have a monitor of the bus that is just listening in, But when I want to use a higher speed, like let's say 10 kilohertz or 20 kilohertz or 200 or megahertz or 4 megahertz, even though the board and difficulties on a breadboard with all the wobbliness and capacity, these capacitances that, all the problems on the breadboards, bad connections, they are nothing compared to the fact that the Arduino Nano is just not fast enough to follow. And when it's not fast enough to follow, while it's okay to not be able to monitor, it needs to at least receive the read requests and throw the wait line fast enough, and this was not possible when I drove a faster oscillator. Which, by the way, this is such an easy oscillator circuit. Take two inverter stages, connect them to each other, connect the output of the first to the input of the second. Output first connected to the input of the second. Here you see that. Put 1 kilo ohm resistors to feed back from the output to each of their input, and then put either a crystal or a capacitor bridging the two, so you can see it. Once you do that, you get a very nice oscillation, and with the crystal it's stable. With a capacitor it's fairly stable, but it's kind of wobbly. So that's what I do, and I want to be able to run this faster than in the super slow mode here. Still happy that I can get the super slow mode done, and it doesn't mess up the registers here, so that's good. This area, what I would like to do now is to have either use dip switches here to do it manually, the switching, instead of these jumper wires, or ideally I could actually program it. So I would have an output register here, which would then have a default state for the memory configuration, but then I can use software to switch the ROM off. And I could use software to perhaps gate the flashing, to have a security on the write line. Perhaps I could do this, maybe not, because that will require 2 more chips. So maybe the flashing I could still do with a mechanical safety lock here, like this one. But changing the memory configuration would be nice, because then we could have a boot routine, a boot sequence that actually does turn off the ROM automatically while the system boots. Obviously, I/O is important, and I kind of feel like I want to build this I/O myself, but I did buy myself a parallel I/O and a serial I/O chip, actually 2 of each. And then I read the manual and found out that I actually should have the clock chip as well, and the DMA chip. So I need 2 more of these chips. And each one, except for the clock chip, is the timer chip. Each one is huge, like this, 40 pins. And it's kind of a lot of wiring than necessary. And I don't know how much I will learn from that. I probably do it if I want to run CPM, but I might want to consider to do the simplest possible I/O, at which I would be able to do input and output, memory configuration, and some sort of disk device. I would like to be able to talk with the system without the Arduino. So if I use the serial input-output chip, then I would have to, and without the clock timer chip, I would be able to potentially use a fixed baud rate clock to have some fixed baud rate, maybe just 9600 bits per second, fixed configuration for the console monitor. That probably is what I would do. But I wonder whether I really want to do this with the Z80 serial input-output, or whether I don't want to just use a shift register. Perhaps, since I anyway need to connect to USB, I wonder why I shouldn't be using some more direct connection to USB. So I don't use an RS-232 emulator, but rather I could hook this up directly to USB as a USB device and run it directly with the USB protocol and hardwire this so that I don't care to drive a modem. I don't care to connect a VT100 terminal. I just want some way of communicating with it, and a blink and light console with toggle switches and LEDs is certainly one thing, but as a minimum, in order to run CPM, I'm going to probably just do the USB. That's a nice project. Instead of a project to wire up standard chips that do standard stuff, which you're not involved in actually making it happen, but just have to wire up according to plan, and then do the rest in software, involved software. I'm more interested in just doing a plain USB connection to this device, and see if perhaps this space allows me to do both the switching of memory configuration as well as some shift register. If I can do it with just a shift register and run the USB that way, that would be awesome. And it could be that this space is enough. Potentially I could sacrifice the 555 timer, maybe not. I could definitely reduce some space here if I really have to, and perhaps this has space, I think, for 1, 2, 3 chips maybe. So it could work. It could work. And then ultimately some sort of maybe a parallel device. Maybe I can use the same thing as I use for the communication with the with USB. Perhaps I just emulate the disk device to the USB channel. Perhaps I do that, and then I could boot into CPM, and that would be the goal. To just have the absolute minimum, just has a Z80 memory, and then the absolute minimum to boot to CPM. Yeah, that's a nice goal. That's a nice goal, but it's not going to happen in this month. Thank you for your attention, if at all somebody watches this. But that's it. Bye. Over and out.